Hello everyone, I'm Brian Macon. Welcome back to the Math Fun Room. In this video we're going to begin learning about ellipses. To start off with, we're going to define the ellipse algebraically and learn about some of the properties of their graphs. Once we do that, we're going to begin looking at some really exciting applications based on some unique properties of the ellipse. So let's get started. All right, let's first consider the definition of an ellipse. An ellipse is the collection of all points in a plane, the sum of whose distances from two fixed points, called the foci, is a constant. An ellipse is sometimes called an oval. My kids like to call it a squished circle because it does not have a uniform radial distance from the center to any point on the ellipse. Let's consider a diagram and label the distances that are referenced in the definition. Now, the definition contains within it a physical way for drawing an ellipse. I'd take a piece of string. The length of the string is the constant referred to in the definition. Then take two thumbtacks that represent the foci and stick them into a piece of cardboard so that the distance between them is less than the length of the string. Now attach the ends of the string to the thumbtacks. And the string is not taut since the distance to the thumbtacks is shorter. So we'll take the point of a pencil and we'll pull the string taut. Keeping the string taut, rotate the pencil around the two thumbtacks, and the path that is traced by the pencil represents an ellipse. Therefore, the distance to any point on the ellipse is constant and represents the sum of the distances to the foci. And with these ideas in mind, we're ready to find the equation of an ellipse in the rectangular coordinate system. So first, we place the center of the ellipse at the origin. Second, position the ellipse so that its major axis coincides with a coordinate axis. In this case, what we're going to do is choose the x-axis as shown in the given figure. Now, if C is the distance from the center to each focus, one focus will be at the point negative c comma 0. And we label this point as f sub 1. And the other focus, f sub 2, will be at the point c comma 0. And it's convenient to let the constant distance that is referenced in the definition be denoted with the number 2a. Then, based on the definition, all points on the ellipse have sum of distances from the foci being a constant equal to 2a. We can write this as the distance from f sub 1 to p plus the distance from f sub 2 to p equals 2a. And we can use the distance formula to find the distance from any arbitrary point p on the ellipse with coordinates x comma y to the focus f sub 1 at the point negative c0. This would be square root of the quantity x plus c squared plus y squared. Now we add to that the distance from f sub 2 to the point P. And again, using the distance formula, we would write this as square root of the quantity x minus c squared plus y squared. All of this is equal to 2a. Now at this point, we would complete about 10 lines of algebra to clean up this expression to get the equation of an ellipse into a convenient form. Now, for the sake of brevity, I'm going to skip the work here in this video. However, you should refer to the textbook to see the work completed for you. It's actually a really fun derivation. We just don't have the time to complete it here. So anyway, after some simplification, we can write the equation in the form x squared divided by a squared plus y squared divided by the quantity a squared minus c squared equals 1. Then one last step we'll take is to write this equation as x squared divided by a squared plus y squared divided by b squared equals 1, where b squared is equal to a squared minus c squared. Now let's just take a moment to consider the geometric interpretation of the relationship that b squared equals a squared minus c squared. Consider our same graph of the ellipse we described a few moments ago. Note that a right triangle is formed with two perpendicular legs. One leg of length c extending from the origin to the focus f sub 2, and the other leg of length b extending from the origin to the y-intercept at the point 0b. Therefore, the hypotenuse of this triangle is the distance from the foci to the y-intercept, and that has a length of a, which means c squared equals b squared plus a squared, or b squared equals a squared minus c squared. Now on this slide, we formally present the equation of an ellipse with center at the origin and major axis along the x-axis. The theorem states, the equation of the ellipse with center at 0, 0, foci at negative c, 0 and c, 0, vertices at negative a, 0 and a, 0, and major axis along the x-axis is x squared divided by a squared plus y squared divided by b squared equals 1, where a is greater than b, which is greater than 0, and b squared equals a squared minus c squared. Now, in this form, the distance to a represents the constant distance referred to in the definition, which also is the length of the major axis between both vertices. Furthermore, note that the foci are a distance of c from the center, the endpoints of the minor axis are a distance of b from the center, and in this orientation, the x-axis is the major axis and the y-axis is called the minor axis. Now, let's consider an example of finding an equation of an ellipse. This problem says to find an equation of the ellipse with center at the origin, one focus at 4, 0, and a vertex at negative 5, 0. Then graph the equation. So we know the equation has the form x squared divided by a squared plus y squared divided by b squared equals 1. Now the ellipse has its center at the origin, and since the given focus and vertex lie on the x-axis, then the major axis is the x-axis. The distance from the center to one of the foci at 4, 0 is c equals 4. Now also, the distance from the center to one of the vertices at negative 5, 0 will be a equals 5. Now we need to find the value of b squared. No, we know that b squared equals a squared minus c squared, which equals 25 minus 16, which is 9. Therefore, the equation of the ellipse is x squared divided by 25 plus y squared divided by 9 equals 1. So we have accomplished the first task in the problem statement, which was to find the equation of the ellipse. Now let's graph the ellipse. In a rectangular xy plane with x and y axes from negative 6 to 6, let's plot the given information in the problem statement. And we're told one vertex is located at the point negative 5, 0, and that means that the second vertex is at the point 5, 0. Now it's standard to label these points in chronological order. So in other words, we have labeled the vertex at negative 5, 0 as v sub 1 and the vertex at 5, 0 at v sub 2. And next, let's plot the foci. So we will plot f sub 2 at the point 4, 0 and f sub 1 at the point negative 4, 0. Now keep in mind the foci are not actually points on the graph of the ellipse. So to sketch the ellipse, we want to plot the endpoints of the minor axis that are a distance of b from the center. Now since the major axis is the x-axis, then the minor axis would be the y-axis. And we had calculated b squared equals 9, therefore b equals plus or minus 3. So we plot the endpoints of the minor axis at the point 0, 3 and the point 0, negative 3. Well, finally, let's connect the vertices to the endpoints of the minor axis. Let's draw a smooth curve from v sub 2 to 0, 3 and from v sub 2 to 0, negative 3. Then let's draw a smooth curve from v sub 1 to each of those points at the end of the minor axis. Now we can check our work using a graphing calculator, but keep in mind in order to do this, we would first need to solve our equation for y. So if we take the equation x squared over 25 plus y squared over 9 equals 1, let's isolate the y squared over 9 term on the left-hand side. We will subtract x squared over 25 from both sides of the equation, and we can write y squared divided by 9 equals 1 minus x squared divided by 25. Now let's multiply both sides by 9 and we get y squared equals 9 times the quantity 1 minus x squared divided by 25. Now at this point, to get y by itself, we're going to use the square root principle and write y is equal to plus or minus square root of the quantity 9 times the quantity 1 minus x squared divided by 25. So in other words, the positive square root will be the upper half of the ellipse, and the negative square root will be the lower half of the ellipse. Each of those equations a function on their own, together collectively making up the ellipse, which isn't a function in its original form. Taking out the calculator, I've already typed in the positive square root expression into y1. So I have y1 equals square root of the quantity 9 times the quantity 1 minus x squared divided by 25. Now I could type in y2 negative square root, but what I'm going to do is take a little bit of a shortcut here. Since I already have the positive root in y1, I'm going to hit the negative key, and then I'm going to call up that equation in y1 by doing the following. So I'm going to hit the vars key. I'm going to arrow to the right one time under the yvars menu. I want to call out a function, so I'll hit the number 1. And then I want to call out the equation y1, so I will then hit the number 1 again to select y1. So now we're back in the y equals screen, and we have y2 equals the negative of y sub 1. This is just a little bit of a time saver to not have to retype that entire expression again involving the square root. So now that I have the equations typed in, I'm going to hit the graph key, and we have the graph of each piece of the parabola. Notice in the calculator, the upper half is colored blue and the bottom half is colored red. Now I am in the standard viewing window, so my window is from -10 to 10 on the x-axis and -10 to 10 on the y-axis. And keep in mind, this is not really a truly square window. The TI's viewing screen is a little longer left to right than it is from top to bottom. So what I want to do is make this ellipse be truly square. And the easiest way to do that is I can hit the zoom button and notice that number 5 is zoom square. So whatever window I'm in, I can choose zoom square and it will square that window for me. So this is really what the ellipse should look like. Notice that the calculator actually is now going from about -14 to 14 in order to square that window. Where this is really obvious is if we were to graph a circle. If we graphed a circle in the -10 to 10 and -10 to 10 x and y axes respectively, it wouldn't really look like a circle, and we would need to square the window to make it truly look like a circle. So anyway, when we're graphing ellipses, we really want to do the same thing to visualize the ellipse in its true form. In this example, we're told to analyze the equation of the ellipse, x squared divided by 9 plus y squared divided by 4 equals 1. Now, for the remainder of our conversation, the direction to, quote, analyze the equation, unquote, means to find the center, major axis, foci, vertices of the ellipse, and then graph it. Now, our equation has the form x squared divided by a squared plus y squared divided by b squared equals 1, where a squared is equal to 9 and b squared is equal to 4. Therefore, the equation represents an ellipse with center at the origin, 0, 0, and the major axis is the x-axis. Now recall that the vertices are a distance of a from the center along the major axis. So since the center is the origin, 0, 0, then the vertices are at the points plus or minus a, 0, which will be plus or minus 3, 0. Now, I like to go ahead and plot the information as we find it and to begin generating the sketch of the graph. So let's plot these points in an xy plane. Here we have an xy grid from -6 to 6 on both the x and the y axes. Let's plot a point at -3, 0 and denote it v sub 1, and then we'll plot a point at 3, 0 and denote it v sub 2. Next, we know the endpoints of the minor axis are a distance of b from the center. So in this case, our endpoints will be the y-intercepts of our graph, and those are at 0, plus or minus b, which will be 0, plus or minus 2. Well, let's plot these 2 points on our coordinate grid at 0, 2 and at 0, -2. Now let's find the foci. We know they are a distance c from the center along the major axis. And for an ellipse, c squared equals a squared minus b squared, which equals 9 minus 4, or 5, for our equation. So the foci are at the points plus or minus c, 0, which will be plus or minus square root 5, 0. Now to get an idea of where to plot these points, if we take out our calculator, we can find the square root of 5. So the foci will lie at approximately plus or minus 2.24, 0. So now let's plot these 2 points in our xy plane, and we will label the focus to the left of the center as f sub 1 and the focus to the right of the center as f sub 2. Now finally, let's connect the vertices to the endpoints of the minor axis, and we will draw a smooth curve from v sub 2 to each of the endpoints of the minor axis, and from v sub 1 to each of the endpoints of the minor axis. Right, in the prior 2 examples, we focused on the major axis being the x-axis. Now on this slide, we present the equation of an ellipse with center at the origin and major axis along the y-axis. And the following theorem states the equation of the ellipse with center at 0, 0, foci at 0, negative c and 0, c, vertices at 0, negative a and 0, a, and major axis along the y-axis is x squared divided by b squared plus y squared divided by a squared equals 1, where a is greater than b is greater than 0, and b squared equals a squared minus c squared. Let's make a few notes here. Notice in this case, the larger denominator of a squared is now underneath the y squared term. This indicates the major axis is vertical. The distance relationships are the same with the ellipse whose major axis was the x-axis. That is, the distance 2a represents the constant distance referred to in the definition, which is the length of the major axis between both vertices. Furthermore, the foci are a distance of c from the center and lie along the major axis, and the endpoints of the minor axis are a distance of b from the center. Now, based on the diagram provided, note that a right triangle is formed with 2 perpendicular legs, one leg of length c, extending from the origin to the focus at 0, c, and the other leg of length b, extending from the origin to an endpoint of the minor axis at the point b, 0. Therefore, the hypotenuse is the distance from the foci to the endpoints of the minor axis and has a length of a, which means b squared equals a squared minus c squared. In this example, we're told to analyze the equation of the ellipse 4x squared plus y squared equals 16. Now, first, we need to match the standard form for the equation of an ellipse. We need the equation to equal 1. So let's just divide both sides of the equation by 16, and we can write the equation as x squared divided by 4 plus y squared divided by 16 equals 1. Now, since the larger denominator is under the y squared term, then the ellipse will have a major axis that is vertical and is thus the y-axis. So therefore, the equation is of the form x squared divided by b squared plus y squared divided by a squared equals 1, or b squared equals 4, and a squared equals 16. So the equation, again, represents an ellipse with center at the origin and the major axis being the y-axis. And recall that the vertices are a distance of a from the center along the major axis. So since the center is the origin, then the vertices are at the points 0, plus or minus a, which will be 0, plus or minus 4. Well, let's plot these points in our xy plane. So using an xy grid from -6 to 6 on both the x and y axes, let's plot a point at 0, -4 and plot a point at 0, 4. Again, moving chronologically, starting from the negative y's to the positive y's, where we're going to label the lower vertex v sub 1 being at the point 0, -4, and then the other vertex being the point v sub 2. Next, we know the endpoints of the minor axis are going to be a distance of b from the center. So in this case, our endpoints will lie at plus or minus b, 0, which is plus or minus 2, 0. So let's plot these 2 points in our xy plane, one point at negative 2, 0, and the other at 2, 0. Next, let's find the foci. We know that they are a distance of c from the center along the major axis. For an ellipse, c squared is equal to a squared minus b squared, which equals 16 minus 4, which is 12 in this case. So our foci are at the points 0, plus or minus c, which will be 0, plus or minus 2 square root of 3. Again, we're just taking the square root of 12, and that simplifies to 2 square root of 3. Now, to know exactly where to plot these points, I could take out a calculator and find that this would be 0, plus or minus 3.46. So let's plot these 2 points in the plane. Again, the point below the center will denote as f sub 1, and the point above the center will denote as f sub 2. So finally, let's connect both the vertices to each of the endpoints of the minor axis with a smooth curve. And we have now graphed the ellipse and provided all the information required to analyze the equation. In this example, we're told to find an equation of the ellipse having one focus at 0, 3 and vertices at 0, negative 4 and 0, 4, then graph the equation. So to begin, I like to plot the information given in the xy grid to begin visualizing the graph. Let's use a rectangular plane with x-axis from negative 6 to 6 and y-axis from negative 6 to 6. Let's plot one focus at the point 0, 3. And then the 2 vertices at 0, negative 4 and 0, 4. Now, since the center of the ellipse is the midpoint between the 2 vertices, then the center must be the origin at 0, 0. Since the vertices are on the y-axis, then the major axis will be the y-axis. And therefore, we know the equation has the form x squared divided by b squared plus y squared divided by a squared equals 1, where the larger number of a squared is underneath the y squared term. Now recall that the distance from the center to each vertex is a. And in this case, we know that the vertices are at 0, plus or minus 4. Therefore, a is equal to 4, and thus a squared is equal to 16. Now, also, we know the foci are a distance of c from the center. Since one focus is at the point 0, 3, then c is equal to 3. So we can plot the other focus at the point 0, negative 3. So next, let's find the value of b that we need for the equation where b squared is equal to a squared minus c squared. And this is 16 minus 9, which is 7. So since we know a squared and b squared, we can write the equation of the ellipse as x squared divided by 7 plus y squared divided by 16 equals 1. And now that we have found the equation of the ellipse as requested in the problem statement, let's finish by graphing the ellipse. And we need to plot the endpoints of the minor axis, which in this case will be the x-intercepts. We know the endpoints of the minor axis are a distance of b from the center of the ellipse. Since b squared equals 7, then the endpoints of the minor axis are the points plus or minus b, 0, which will be plus or minus square root of 7, 0. And in a calculator, we can estimate square root of 7 to be approximately 2.65. So let's plot a point at negative square root 7, 0 and positive square root 7, 0. And now that we've plotted the vertices and the endpoints of the minor axis, let's connect these points together with a smooth curve, and we have the graph of the ellipse. Let's make a quick note about the connection between an ellipse and a circle. Now, technically, a circle is a special kind of ellipse. To understand why, let's consider the equation of an ellipse of the form x squared divided by b squared plus y squared divided by a squared equals 1. Now, on the right-hand side of this slide, we have an ellipse whose major axis is the y-axis, being represented by the equation that we just wrote. So the vertices are on the y-axis and the 2 foci are also on the y-axis. In this diagram, we've also labeled a point P on the ellipse. We can see two dotted lines, one from f sub 1 to the point P on the ellipse, and another from f sub 2 to the point P on the ellipse. Keep in mind the sum of those two distances equals 2a, the constant distance referred to in the definition. And we can make the same connection with a vertical ellipse or horizontal. So now let's consider the case where a is equal to b. So our equation becomes x squared divided by a squared plus y squared divided by a squared equals 1. Now if we multiply both sides of this equation by a squared, we convert it to the form x squared plus y squared equals a squared. And this is the equation of a circle with center at the origin and a radius of a. Now furthermore, we can calculate the distance the foci are from the center as c squared equals a squared minus b squared, which would be a squared minus a squared, or 0. So in other words, the foci are a distance of 0 from the center, or the foci is at the center. Now graphically speaking, this means that the closer the foci are to the center, the more the ellipse will look like a circle.